The daytime stopped. Stories from a black hole. Imagine watching someone fall into a black hole. From your perspective, they slow down as they approach the event horizon. Slower, slower, until they appear frozen in time, forever falling, never crossing the boundary. But from their perspective, they cross the event horizon in seconds and plunge toward the singularity, where time, space, and everything they know cease to exist. Welcome to the strangest phenomenon in physics, gravitational time dilation at a black hole's event horizon, the place where time stops. What is the event horizon? The event horizon is the boundary around a black hole beyond which nothing, not even light, can escape. Once you cross it, you're committed. There's no turning back. But the event horizon isn't a physical surface. It's a mathematical boundary in spacetime where gravity becomes so strong that escape velocity exceeds the speed of light. And near that boundary, time behaves in ways that break our everyday understanding of reality. Time slows down. Einstein's general relativity tells us that gravity warps spacetime. The stronger the gravity, the slower time moves relative to an outside observer. Near a black hole, this effect becomes extreme. If you hovered just outside the event horizon of a supermassive black hole and your friend stayed far away in flat space-time, you'd experience time normally. But your friend would see you moving in extreme slow motion. Your clock would tick slower, your heartbeat would slow, your words would stretch into an endless, deepening hum. If you spent 1 hour near the event horizon and then returned to your friend, they might have aged years or even centuries, depending on how close you got. The frozen astronaut. Now imagine you're falling into a black hole. From your perspective, you cross the event horizon in finite time. The stars behind you redshift and dim. The universe ahead compresses into a shrinking circle. You pass the point of no return and continue falling toward the singularity. But from your friend's perspective, watching from a safe distance, you never cross. As you approach the event horizon, you appear to slow down. Your image redshifts, your light stretches into longer, redder wavelengths. You fade from view, becoming dimmer and dimmer as photons struggle to escape the black hole's gravity. Eventually, you freeze. Your last image is permanently etched onto the event horizon, a ghostly silhouette slowly fading into darkness. You appear stuck at the event horizon forever, even though, from your own experience, you crossed it long ago. The paradox. This creates one of the strangest paradoxes in physics. From your perspective, crossing the event horizon is an event. It happens at a specific moment in your timeline. But from an outside observer's perspective, that event never occurs. You asymptotically approach the horizon but never reach it. Both perspectives are true. Time is relative. There's no universal now. What you experience and what others observe are fundamentally different, and both are correct within their own reference frames. Spaghettification. But there's another problem: tidal forces. Gravity near a black hole doesn't pull uniformly. Your feet, closer to the singularity, experience stronger gravity than your head. This difference, called tidal force, stretches you. For stellar mass black holes, a few times the sun's mass, tidal forces are catastrophic. Long before you reach the event horizon, you're torn apart in a process called spaghettification. Your body stretches into a thin stream of atoms. For supermassive black holes, millions or billions of solar masses, the event horizon is much larger and tidal forces at the horizon are weaker. You might cross the event horizon intact and survive, briefly, before tidal forces deeper inside rip you apart. Inside the event horizon. Once you cross, the rules change. In normal space-time, you can move freely through space but are dragged forward through time. Inside the event horizon, those roles reverse. You can no longer move outward in space. All paths lead toward the singularity, but you can, theoretically, move backward and forward through time. The singularity isn't a place, it's a moment in your future, an inevitable endpoint you cannot avoid, no matter what you do. And at the singularity, space-time curvature becomes infinite. Our equations break down. We don't know what happens there. what would you see? As you fall, the universe behind you speeds up. Stars age, galaxies evolve. If you could survive long enough, you'd watch billions of years of cosmic history unfold in moments. But you wouldn't survive. The singularity awaits. The firewall paradox. There's another twist. Some physicists propose that the event horizon isn't empty space. It's a firewall, a region of intense energy that incinerates anything crossing it. This idea comes from trying to reconcile general relativity with quantum mechanics. If the firewall exists, you'd be destroyed at the event horizon, never reaching the singularity. But we don't know. We've never observed anyone fall into a black hole. We've never sent a probe across an event horizon. The lesson. Black holes don't just bend space, they bend time. They create regions where the flow of time is so distorted that reality itself splits into incompatible perspectives, where an event can happen and not happen simultaneously, depending on who's watching. The day time stopped isn't a single moment. It's a boundary, a place where our understanding of the universe reaches its limit and the rules of reality change. And if you ever find yourself near a black hole's event horizon, remember, from your perspective, time marches on. But to everyone else, you've already become part of the past, frozen forever at the edge of oblivion. Like, share, and subscribe for more cosmic mysteries. And as always, keep looking up.